Thank you very much, Ming, and I'll start right away with my talk. This topic has been a focus of mine for the last 17 years or so. So if you want to be successful in any project, you have to spend 17 years on it, or at least 17 years. A little bit about the clinical background. This should be of interest to everyone because this is the colorectal cancer is the second leading cause of cancer death. And here you have some numbers. 130,000 new cases in the US, 55 to 60,000 die every year in the US, and 700,000 die around the world every year from this disease. The disease really starts from polyps that grow very slowly, about 1 millimeter a year, and only when they get to about 10 millimeters and over, they become malignant. So you have 10 years before to detect it. And if we indeed ask everyone of the age of 50 to go and screen themselves, we can save 91% of colorectal cancer. We can save 600,000 lives every year in the world. So this is really an important mission. The current gold standard procedure is optical colonoscopy, where the doctor introduces a scope through the rectum and checks the entire length of the colon. This is accurate to about 5 millimeters, but it's a very invasive one, very risky. There's about 1 in 1,000 that get perforated and need to go immediately to a surgery, and 1 out of 5 of those actually die. So 1 in 5,000 chance to die from this procedure. So there's some risk there, but it's the gold standard. And the more troubling issue with that it examines only 3/4 of the colon surface. 25% is not being examined, and I'll explain to you how we can do it with the alternative procedure. And the alternative is what we call virtual colonoscopy. What we do is we take a CT scan of the abdomen, several seconds, and it used to be when we started 17 years ago, 50 seconds or so with a spiral CT. You have to hold your breath for 50 seconds, and then we take a CT scan of the abdomen. Nowadays, with the 64-slice CT, it's 7 seconds. With a 320-slice CT, it's 1 second. 1 second a scan, you turn around, another second, and you're out of that. In virtual colonoscopy, we automatically segment and reconstruct the 3D model of the colon and then give the doctor a tool to navigate inside the colon, very much like a video game inside the colon of the patient. We use real-time volume rendering and navigation for that purpose. The advantages as compared to optical colonoscopy, this is a much safer one, non-invasive. Accuracy is really the accuracy of the CT scanner, which is sub-millimeter. We evaluate the entire colon surface. As I mentioned before, in optical, it's only 75%. It's relatively inexpensive, at about half the price of optical colonoscopy, very fast. You can't compete with the second, another second, and 15 minutes you're in and out of the radiology suite. It's comfortable preparation that I'll talk about it because this is the main complaint of people that go through optical colonoscopy. The prep is ugly. And this one is much better. And we have a complete electronic record, which is also very important now that we go more and more into electronic medical records. The technical advances that we went through the years is automatic segmentation and automatic electronic cleansing. You don't have to sit in the bathroom the whole day. The computer does it in a few minutes. We do real-time volume rendering. We do electronic biopsy. I'll talk about it a little bit later. Basically, giving you a tool to determine right there on the screen if there is a chance of this polyp to become malignant. It's interactive navigation, and it's definitely very fast. So what are the steps? We have to do first some kind of bowel preparation that I'll talk about. Then we go through the CT scan the next day. And then the computer is doing some pre-processing. Typically, it's done on a server in the corner. It will do the segmentation, the electronic cleansing, the 3D reconstruction. We generate a center line, medial axis of the colon, and we compute a potential field that help us in the navigation. And only then we have the navigation, which is done kind of on a client. What is the bowel preparation? There's 3 meals in a box. This is the box that you get. It's typically low residue diet with applesauce and crackers and things like that. And then 3 bottles, which are banana smoothie with barium in them. And the barium basically tags or paints the leftover in the colon very bright, so it's being picked up easily by the CT scanner. This is very minimum cleansing. It liquidifies. Typically, the barium liquidifies the stool, so we have puddles of liquid inside the colon, and that actually helps us in the segmentation. Then we go through the CT acquisition. Typically, the next morning, you can use, as I mentioned before, a single slice or multi-slice. It takes anywhere between 1 and 50 seconds, depending on the machine. We do take supine. You lie on your spine or you lie on your stomach, and I'll talk to you about how to register the 2 of them a little bit later. A typical CT scan of this is 512 by 512 by 1 millimeters, although there are higher resolution of that. And this yields anywhere between 300 to a few thousand cross-section slices, and you get a lot of data, a gigabyte, 2 gigabytes, and that's what we have to deal with. So this is a sequence of slices, although what you see in here, the black area, is the colon, and this already cleansed. So what you see, the black is air inside the colon. The doctor used to take this and go through the slices, and every time they see a small bump in here, they think that might be a polyp. So they have to go back and forth between the slices and mentally reconstruct the 3D. It's a very difficult process. This is what it looks like before the cleansing. You see a puddle of liquid tagged with barium. We have several of them, including the prone. You see the gravity. This is gravity going up. That's how doctors like to display them. Both of them are the same. This is the spinal cord. The spinal cord, although you lie on your stomach. Anyway, we take a supine and a prone, and I'll show you later on how to register them. In the pre-processing stage, as I mentioned, we do electronic cleansing and segmentation. We compute the center line. We compute potential fields. And then we generate an electronic model for this particular patient. The segmentation, what we would like to do is in the electronic cleansing, what we would like to do is to remove these puddles of liquid and to reveal the mucosa. But we have to reconstruct the mucosa, because right now we have a partial volume effect between bright liquid and the muscle. And what we would like to reconstruct is something between the muscle and air, which is dark, like that, or black. So this is the main challenge. The way we do it, we do region growing and labeling, and you get this kind of labels, air and fluid. And you get also the boundaries between fluid and air, between fluid and the muscle, which are of important to us. Of course, you get other boundaries and other groups. In order to generate or reconstruct this partial volume effect, we use we remove that liquid and we go through a process we call intensity flipping, which is basically, instead of gradient from white to gray, we go from black to gray, which is very easy to do. We also have to worry about these handles that we get because the surfaces are too close to each other, the folds are too close to each other, and sometimes the colon folds around and touches another part of it. And so we have to go through a process of topologically denoising it or cleaning it and get the surface to look like that. We can deal with higher genus surfaces, but it's much cleaner to have it denoised before we start the process. And from here, we basically generate marching cubes surface of the entire colon. Here you can see what this looks like when you fly, and there's a whole puddle here of liquid. And this is after the liquid was cleansed, and you can see this fold and that fold revealed underneath that puddle. And the main goal is not to remove any of the polyps that we have underneath or possibly have underneath the liquid. When we do the segmentation, I want to emphasize we do this flooding, and what we generate is the mucosa surface. As Steve told me today, this is the egg, not the eggshell. So we're looking at the colon from the inside, and that's the surface we reconstruct here. There's another project altogether that we generate the outer layer, and actually we get the volumetric thickness to this column. But I just want to mention this. We also compute the center line of the colon. This is kind of the medial axis. It guides the navigation. So if we leave the virtual camera right here, it will slowly drift all the way from the rectum to the cecum in the middle of the colon. And along the medial axis, you have the best field of view. Still, you see only 75%, as we mentioned before. Well, we'll talk about it a little bit later. It also gives you some idea about the measurement. If you find the polyp around here, you can say I'm 13.3 centimeters from the rectum. We compute two potential fields. One is distance to boundary. So the main point of this is a collision avoidance. You do not want to collide and definitely not penetrate the boundary. So if we have a very high potential by the walls, that basically pushes you back to the center. So again, as I said before, if we leave the camera by itself without interaction, it will navigate along the middle of along the center line. We also have distance to target that basically pulls the camera, the virtual camera, from the beginning to the end, from the rectum to the cecum, and then we can turn it around. The navigation is physically based, and the automatic fly-through is from the rectum to the cecum and back. That without external forces. Of course, we can apply external forces and get closer to a polyp, examine it from different orientation, and we kind of simulate a submarine inside the liquid. We used all along volume rendering, and I'm not going to elaborate on that. We got it on a PC anywhere between 10 and 30, and that's even in our SIGGRAPH paper in 97, 99, 2002. These days you can get much faster. But the most, and you get, of course, more realistic images with that. But the more important one, that volume rendering really supports our electronic biopsy that I'm going to detail a little bit later. As a comparison, just to show you what it looks like in optical colonoscopy, every time the gastroenterologist sees a polyp, they take a snapshot of it that looks like that, and they mark it on a diagram. This is a diagram of the colon. In virtual colonoscopy, this is the volume rendered image of the surface of the polyp, and this is the exact location on a reconstructed model of this particular patient. And this is a 4 millimeter polyp. An 8 millimeter polyp looks similar. This is a snapshot by the gastroenterologist, and the marking, this is a rectal polyp. And here it is in the virtual space, again, marked in the exact location. We can also find these diverticuli. These are kind of cavities. It's a disease that you have to worry about, and virtual colonoscopy can find this type of disease as well. We can do 3D measurement. The size of the polyp is a good indication of how clinically significant this polyp is. If it's definitely in this size of 7, 8 millimeters, you should be taken out and sent to a pathologist. We have also another tool to help us to decide whether this is malignant or turning malignant or not, and this is the electronic biopsy. For that, we use translucent volume rendering, and this lets us look into the polyp. And we can use that to distinguish leftover stool from a polyp. We can use it to distinguish different types of polyps. I have several examples. So this is the stool ball. This is a surface view of a stool ball. Looks similar to a polyp, but if you examine the inside, it's uniformly tagged high. And red is high, blue and green are low. And the reason it's uniformly tagged high because the barium was incorporated into the stool, and it looks uniformly high. This is a hyperplastic polyp. Hyperplastic means it's benign and will not turn malignant, and you can see it's kind of uniform, and it's green and blue. However, if you look at an adenoma, which is going to turn malignant, it shows you that there is some high densities here, this reddish areas that we see, and it's irregular. And that tells you this is a suspicious polyp and should be taken out. And another example is another kind of adenoma, again, irregular reddish areas. I mentioned before that in optical colonoscopy, yes?
The color came from the shape analysis?
No, the color came from integration along the ray for volume rendering into the polyp. So what we're doing is basically volume rendering with translucent transfer function. And the mapping to red, green, and blue is an arbitrary mapping that we did. So these are artificial colors, of course, but we have a certain scale. Red is a high density, green and blue are lower. Okay. So here we have a tool that allows us or supports the visualization or examination of the entire surface of the colon. In the optical colonoscopy, we have 75%. The same thing is here. When we fly from the rectum to the cecum, we typically see around 75% we have to turn around and repeat this from the cecum back to the rectum. We have a tool to help us in that, and we call it painting, and we basically go ahead and paint the surfaces that we've seen. This is about 75% of the colon has been examined. This is the red, the green area. The red is still to be examined. And that's what it looks like if you turn around. There's a lot of patches that we missed. Why we missed the patches? Because we have these haustral folds that hide certain areas or patches. And also when you have these sharp turns, you have also areas that yet you miss. You have a limited field of view inside this cave or tunnel, and you don't see everything. So 70 to 80% you see as you go in one direction. We paint it green, and then we turn around, and you can go as high as 95% or more. And then if we still have some missed area, we can step through them one by one. So we can get to 100% surface coverage. And this is called a complete colonoscopy. What the gastroenterologists do is an incomplete colonoscopy. The user interface that we developed for the doctors looks like that. It's a relatively simple one. You have in the middle this endoscopic view. That's where the main window. We have the sagittal, coronal, and axial views here with a lot of data. For example, we are at location 118, 222, 185 inside this volume. You have the 3D model reconstructed with a 3D cursor. This 3D cursor also appears in there. And we have here a view just in front of the camera. So this is a view just in front of the camera. And a very few buttons. That's all the doctors wanted. Very few buttons. So I mentioned to you this problem of supine-prone registration. We want to have correspondences between them. For example, if I go and examine the supine and see something that I'm not sure about, I would like to go and confirm it in the prone. So I need to have a way to press the button and say, get me to the other scan. This is not very trivial because the colon changes substantially from one scan to the next one because we compress the stomach when we lie on our stomach, and the whole colon shape is changing. Here you see an example of that. So the way we did this, after some pre-processing, we found some landmarks in one and the other one. And we used that to register the two of them and map each one of them to a rectangle. So you map the supine to a rectangle, you map the prone to a rectangle. And beyond that, we have a registration, but it's not a very good one. It's a reasonable registration, but a very good one. Then we go and find feature point, which are curvature extrema, and we use that to further register the supine and prone with harmonic map registration, which is kind of quasi-conformal. So you don't really lose any shape structures when you do that. And that's how you get the supine-prone registration. What are the anatomical landmarks that we identify? We have these 5 areas colored in different colors here. The ascending, transverse, descending, sigmoid, and the rectum. And we basically divide them into these 5 segments, and each one of them is a landmark. And then we identify the tinea coli. The tinea coli is kind of muscle that go on the surface of the colon. And there are 3 of them. We take one of them, and we use it to actually cut the colon along that line, and we lay it open. So we have it for the supine, we have it for the prone. We cut them open, and we use these deflectors to register them. So that's how we do it. We take one segment, map it to a flattened colon. That's what it looks like. And that's just to show you that it's angle preserving because it's conformal, because it's angle preserving, it's shape preserving. And then we go through the feature detection, and we find this extrema point, and we match the point, and we use that to do a finer matching. So this is the result of the conformal mapping without this additional feature point. With that, you get a slightly better correspondence between the supine and prone. By the way, this is also a way to examine the colon. You have it, the entire colon open in front of you, and you don't have issues of any hidden parts, no haustral fold or bends hiding parts of the colon. But the doctors don't particularly like this way of looking at the colon. Maybe they'll get used to it. Anyway, the registration result that we got was an average of 7.8 millimeters. And here you see some examples. This is the 2D. This is a 3D view of the same. So you see the folds, and you see the polyp here and there. So this is a reasonable registration. All we want is if you see something that you're not sure about, you can jump to the other view and confirm it with that. A little bit of a pause, just the history of virtual colonoscopy at Stony Brook. I told you I started 17 years ago in 1994. We did Phantom, basically a respirator pipe and a few eraser that we cut at 3, 5, and 7 millimeters, and we immersed in water and scanned it. All of that came out nicely. Then we took the visible lumen, and we found the polyp in the visible lumen, and it was on the NIH, on the cover of the NIH report, the visible lumen polyp. In '96, we did our first prototype with patient, and we published it at SIGGRAPH. 2000, we licensed it to a startup company, Viatronics, which I helped to launch. For a year and a half, I spent a year and a half of my life setting this up. We got FDA clearance, which and then commercialized that. Just recently, we licensed it to Siemens and other companies, and because this is a public presentation, I can't tell you which are these other companies. They don't want you to know. But Siemens is definitely a nice partner to be in this mix. Viatronics has sold hundreds of systems. Siemens and the others are selling thousands of systems. So there are many thousands of these systems around the world. And if each one of them is doing even one patient a day, they typically do more. We're getting a lot of thousands of people scanned every day and saving a lot of lives because of that. So as I said, we licensed it to Viatronics and Siemens. So here's a video of a small polyp. That's about the speed that the doctor see it. And now because we saw some bump on the wall, the doctor is using the mouse to navigate and try and get a good view of that, and using lighting also to help you to see this is indeed a bump and not a diverticulum. Another video I'll show you with this, a larger polyp, and we will do an electronic biopsy of that. So we saw the polyp, and now we're turning around to get a good front view of it, and now we apply this electronic biopsy on that polyp. And I have one more example with the electronic biopsy. You go around this bend and this one, and you see the polyp right there in front of you. You can't miss it. It's a relatively large one. So we'll turn around, we'll bring it to a nice view and perform this electronic biopsy. So we started, of course, we did our clinical studies. We did with 161 patients. A lot of them were trying this idea and that examination. So we had only 62 of these that were consistent, and we could use them in a study. And, you know, that's what we got. This is a reasonable, encouraging results that we do with the virtual a little bit better than the opticals. Big ones everyone finds. The issue is really with the smaller polyps. Then we were providing the support and the software to a large Army study. This was done in 2003. The Army literally started this project on January 2003. They bought a CT scanner. They recruited 1,200 generals. These are Army people over the age of 50, so most of them were really generals. And it was done through in several hospitals, Army hospitals around the country. And already in December 1, they published a paper in New England Journal of Medicine. So this is extremely fast for the Army. And they got pretty good results. The sensitivity was at the 94% as compared to optical colonoscopy, which is several percentages lower. The more anecdotal results were that there are two big malignant polyps. Both of them were detected on the virtual colonoscopy, and one was missed on the optical. I don't want to say this is not because optical was not good, because this was the polyp. It was 16 millimeter, a very large polyp, as you can see in the virtual. But it was right by the cecum. So the cecal polyp near the appendix, that arrow is showing the appendix. And that's what it looks like in the optical. They went again and looked at it and removed it, and it was indeed malignant. And that's what it looks like in a slice. So this is an example of one of these polyps. A more recent study, which was twice as big, was the ACRIN clinical trial. They had a lot of hospitals involved in that, and they also published the New England Journal of Medicine paper. And they were looking only at large and medium-sized polyp. They were not looking at the 3, 4, 5 millimeters polyps at all. And they said that VC is comparable by effectiveness to optical colonoscopy. They were working with gastroenterologists, and that's the maximum they could say in their result statement. Anyway, let me spend a few minutes talking about CAD. You know, CAD is an overloaded acronym, but yes?
Can I just quickly ask, you were giving percentage detected for both schemes, but then what is the ground truth? Is that the union, or what is, I mean, when you say 90% or 93%?
No, each study has the pathology as the ground truth. So you have to go and you know, confirm it. So if indeed it was, yeah. So each study has its separate ground truth.
Not clear. Now, don't only do pathology on things that you think might be polyps.
Right.
So the question is, if there are polyps that neither one saw.
Oh, no, okay. Right. I don't know anything about those. But these both studies, I didn't mention it, I'm sorry. In this study, all these studies were done with virtual colonoscopy followed by optical colonoscopy on the same day. So you had this comparison, and definitely the optical colonoscopy, when they saw something, they took out and examined it in a pathology. So that's all the.
The question I think that isn't clear to me is when you say it has 94% sensitivity,
that presumably means that 94% of the polyps over 8 millimeters, or whatever the threshold is, it detected.
Okay.
How do you find the 6% that it did not detect?
For example,
Both of them seem to have sort of one head, and one of them, a little bit lower, one was a little bit higher. The question was, what is the 100%? What are the few percent that are not right? Right there. I think that was your question, right?
So I'm not sure what they did with the optical, but I know with the virtual colonoscopy, they compared it to optical and the pathology. If they had a pathology and the polyp that they found in the optical and went to pathology and indeed was a polyp and was not found in the virtual, that was classified as a miss. I don't know how they characterize the optical colonoscopy sensitivity. Maybe it's compared to, maybe these are numbers that they didn't come from this study. They came from the literature or something like that. I'm not sure. I know that this study was a virtual colonoscopy study, and these are the results that they reported, and this is just a comparison base. Yeah.
Use the ground truth to be the pathology, right?
In this field, the ground truth, the gold standard is indeed the optical colonoscopy. That's how it works. It's the optical colonoscopy combined with the pathology. This is the ground truth. This is the gold standard.
You're not going to cut all your
No, you're not going to do that. Anyway, this is. We need to read this New England Journal of Medicine paper again to figure that out. Anyway, CAD. So in CAD, what we want to do is to automatically detect polyps. And most of the techniques that are out there are using shape-based, which is a pretty expensive technique. You have to examine the entire shape of the colon surface and try and figure out if you have these rounded objects there. And the main goal is not to replace the radiologist at this stage, but have a second reader or a second set of eyes to complement the radiologist. Maybe in the future we'll have it as a sole reader, but the FDA will have to approve that. We know that two doctors do better than one, and a computer and a doctor do better than two doctors. So there's a good chance that this will be a better fit. Anyway, the technique has the following steps: segmentation and extraction. We already spoke about that. We do again a conformal colon flattening that you saw, and then we perform electronic biopsy on the entire colon, and we do clustering in the 2D space after this electronic biopsy. We do some false positive reduction because we have too many of them, and then integrate it in the virtual colonoscopy user interface. So as I said before, we spoke about the segmentation and surface reconstruction. What we do here, we take the entire colon and cut it along the tinea coli, flatten it using conformal mapping, map it to a rectangle. This is important because a lot of these map it to some other shapes. And we need a wraparound, because if you have a polyp right here, which is there, it's a good idea to have a little bit of overlap. So it is angle preserving, as I mentioned before. Here you can see what the 2D view after the conformal mapping looked like, and this is the 3D view. So this is the blue line is this Tinea coli that we're cutting along it. Once we do that, we perform an electronic biopsy on the entire colon. This is, I believe, the rectal area and going forward, and this is still half of the colon. It's a very, very long organ. And we typically generate an image which is about 4,000 by 200 pixels. 4,000, very long, by 200. And we can generate it anywhere between 100 to 500 milliseconds on the GPU. So the entire colon can be volume rendered with that kind of speed. So you see most of the colon looks like very benign. It's blue and green and yellow. And from time to time, we have areas that are a little bit brighter, and they are suspicious of being malignant. We have some details here. How do you generate the rays? How do you find out the normal for these rays? Because you do volume rendering, and when you terminate these rays, because this is only a surface, the data is separate from that surface. We have now another piece of work that we actually have a thick surface, and we map it to a cuboid, and then you know where to start, where to finish, and what is the normal, but that's separate. So here, for example, there's an area that has some reddish in it, and it's irregular, and it's suspicious of being a polyp. So after we do this volume rendering on the entire colon, we do clustering. And we found these areas that have this reddish neighborhood. And we look only of those that are larger than 5 millimeters, because below 5 millimeters it's not clinically significant. And then we have to reduce some of the false positives, because there's a lot of them, and the doctors would not want to look at 30 or 40 of them, so we want to reduce it, and we do the reduction by looking at shape features. And we just look at shape index and curvedness. You can look at others, and that helps us to reduce the numbers. And again, I want to emphasize, we're not doing shape analysis on the entire column. We're doing shape analysis only on those that we found in the clustering algorithm. So let me summarize this. We do take the 3D surface and flatten it to a 2D. That makes the clustering much simpler, to do a 2D clustering rather than clustering in 3D space. And after the clustering, we do some false positive reduction, and we get a few, somewhere below 10 suspicious areas that the doctors can go and examine. So that's what it looks like, electronic biopsy, a lot of potential suspicious areas, and then after the false positive reduction, we have a few of them. It's the end only A is a polyp, B is not, and that the doctor needs to actually examine. We incorporated it into a virtual colonoscopy interface. You can do different things. As you navigate through the colon, you can highlight it by color, by sound, or you can basically put a bookmark on the 3D model overview, which is on the left-hand side of the user interface on the flattened color image. Here you can see it. Either you can mark it on this area or in this flattened view. This is the current position where we are in the colon. So you can examine the colon using this one, this one, this one, or if you want to go the old way in one of these slices. CT data that we used some of the National Institute of Health, and some from Stony Brook Hospital. So we used a total of 98 data sets in here. That's to give you some idea about the timing. Segmentation, colon extraction is at 3-4 minutes. The most expensive part is the conformal flattening, which this is not accelerated by any way. So after acceleration, we get it in less than 7 minutes. The biopsy, I told you, that's about 300 milliseconds. The detection, the clustering is fast, and the false reduction is fast. The interesting part is the how many false positive reduction we do per data sets. You get there 96, 97%. So far with this data set, we got 100% sensitivity. I am a little bit embarrassed to point it out, but we are continuing to look through our data, and we have 1,000 of them. So I'm sure that we will find cases that are not. And again, the sensitivity here is compared to the biopsies that we have. Yes?
The 100%, that's simply fabulous. So does this mean that the radiologist could just look at the ones that you mark suspicious? It's 100%.
Yeah.
You can't do better than that.
Yes.
How much time does that save the radiologist?
About you know, depending on the way you construct the virtual colonoscopy. If we do have it's part of the navigation system, so the doctor indeed is looking through the entire colon. That doesn't save much, maybe a minute. But if we do it as a bookmark and you step through them, that can save, 7-8 minutes.
How long does it
Typically, an examination takes approximately 10 minutes. So they go in one direction 5 minutes, go back in about 4 minutes, and then another minute spending on looking at polyps. So if you can help them in that process, as I said, it's at least a minute, maybe much more. I'm not suggesting that this is just preliminary result that we got only about on 90 or so data sets, and we have about 1,000 that we plan to examine, and I'm sure that we will find things that are not 100%. Okay, a few more minutes. I want to show you a more recent work that we did with our cave that we call Immersive Cabin. This is a 5-wall cave which has a door here that you see the door that closes. So this is it's a nice system because you indeed get immersed and even get lost inside this 4 complete walls. And that's what it looks like inside the colon of a patient. So we have a floor and we have 4 walls around you, but we're missing the ceiling. And the question is what to do with that missing ceiling. I'll describe it in a minute, but why this is very helpful. So if you remember, if we look at the finite screen, we may miss polyps which are behind folds or around sharp bends. If we have a way to look at the right wall or the left wall or the floor, every time that this polyp is behind this fold and we missed it here, when it gets to this point, we're going to be able to see it. Think about going down, I don't know what's the main street here, and you get to the corner, you can look to the right, down that street, and to the left, down that street, and basically reveals everything in that fold. So we're not going to miss anything in these folds. Again, this is a prototype. We started to work with 3 radiologists, saw that, and they liked it. but we're not sure exactly how this will work out. Maybe with a swivel chair in the middle, because they can also look backward and see what they missed. We don't want them to get lost, so you have to give them some kind of an orientation and directions there. Anyway, so what do we do with the ceiling? So if you have, this is the front view and this is the ceiling, we divide the ceiling into 4, and we basically squeezing this area into this wall. Okay, and this is using, again, conformal mapping, so shape looks similar. So this is what the front view would look like when we add this area from the ceiling. So that would look like before we squeeze the ceiling in, and that's after we squeeze the ceiling. So you get the general idea of the same shape, and polyps will indeed show in this area, but we're not missing the ceiling. So you can see some bumps here that might be polyps or not. So I have actually a video here. Yeah, we can watch the video as we talk. One second, let it start, and I'll explain what it is. So that's the top. This is the front, and that's the front after this squeezing of the ceiling. Yes, Henry.
If you can squeeze the ceiling that's missing into the front wall and claim that, is that what you're doing?
Not in the front wall. I divide the ceiling into 4 and squeeze it to front, side, and back. Okay? So you can see that basically we're taking part from here, from the ceiling, and mapping it to the front view. So this is actually a VR 2011 paper that we got in. Okay, so let me summarize. So virtual colonoscopy is not supposed to replace optical colonoscopy. It's just a mass screening for colon cancer. For example, in this Army study, only 8.5% or so really needed an optical. All of them went to the optical because this was the Army regiment, but in that particular study, only 8.5%. In Stony Brook, we found it more close to 20%. And if you go to smokers or high risk population, it can go even higher. But let's assume it's an average of 10%. Then the other 90% can go home without any invasive procedure. So we see that most of the study actually confirmed that it's better than optical colonoscopy, and it's safer, non-invasive, comfortable, primarily because of this prep. You don't have to go to this drinking a gallon of Golightly. And you can see 100% of the surface. It's more accurate. It's inexpensive, as I said, half of the price, and faster. And we have all of these nice technical features that we incorporated to it. This is really a successful medical application, and I know many of you work in medical application, and that's probably at least my satisfaction from working in this area, that I see that we can save lives. And I showed you a more recent work on stereo and CAD. Of course, these both of them need more work to do. And I showed you several of our publications, but our best publication was in the New Yorker about that, and this was in 2004. So this was really the best day of my life. I was very happy to see that I got a paper in the New Yorker. Of course, this is not my work. We had a lot of people, a lot of funding going through this. 4 other faculty and 3 doctors. A lot of postdocs and PhD students worked on that, and I thank them all. And I thank you, too, for your patience.